4.7, the law of sines and law of cosines. In this unit, prior to learning how to generate and use the unit circle to find trig ratios for special angles and to generate the unit circle in radians and degrees, we learned how to solve right triangles, both for sides and angles, using SOHCAHTOA, sine, cosine, and tangent.
Can I get a
Today we're looking at non-right triangles. So we're going to be able to solve oblique triangles using law of sines. And then in our next section of this lesson, we're going to learn how to solve them using the law of cosines. And then, so we're going to be solving using the law of sines and cosines. And then when we look at law of cosines, also look at how to find the area of oblique triangles. Because it's great to use half the base times the height. It's great to use half the base times the height to find the area of oblique triangles. But you can only do that if you have a base and height that are perpendicular. If you don't, you have to use a different formula. So what is an oblique triangle? Let's look at the definition right here. An oblique triangle is a triangle with no right angle. So it's a non-right triangle. It could be an acute triangle, or it could be an obtuse triangle. So we could have one obtuse angle, or we could have all three acute angles. So, but you remember triangle sum from geometry that all the angles in the triangle have to add to 180 degrees. So for your notes, you can just put the oblique triangle is a non-right triangle. So if it's a right triangle, we're just going to use SOHCAHTOA to solve for sides and same thing to set up ratios, inverse to find angles. But if it's not a right triangle, or if we don't know if it's a right triangle, then we're going to have to use either law of sines or law of cosines. First one we're going to look at is law of sines. The law of sines says that the sine on a triangle, on any triangle, we're going to call this triangle ABC. The sides opposite of each letter have the same letter. So if this is angle C, then this is side C with the lowercase. If this is angle A, then this is side A with the lowercase. And if this is side B, then this is side B with a lowercase. This rule says that sine of angle A, whatever that ratio is, divided by the length of side A, will be equal to the sine of angle B, whatever ratio that is, divided by the length of side B. And each of those will also be equal to the sine of angle C, whatever ratio that is, divided by the length of side C. This is the law of sines. You pick any two of these fractions, set them equal, and you have a proportion. That is the law of sines. So in order to solve this, I either need to have two angles and one side, so I can solve for another side, or two sides and one angle, so I can solve for an angle. Solving the triangle, we're going to go around the side length to the nearest 10, and the angle measures to the nearest 3. It's supposed to be applying the law of sines. In this case, we've been given two angles, which is awesome, and we're supposed to find two sides and the third angle. The third angle is easy enough to find because we're just going to use the triangle sum theorem. So 180 minus 51 minus 63 gives us 66 degrees for angle T. Now we're going to need that not only as part of our answer, because we have to find the three things that weren't given, the measure of angle T being 66 degrees, but now because we need to use that to set up our ratios. The only given side and angle pair is the 13 and the 63. Those are opposites. So as I solve for S, I'm going to have to use the sine of 63 over 13 to set up and solve for both of those. Sine of 63 degrees over 13. When I'm solving for side T, I have to use angle T. So sine of 66 degrees over side T. When I'm solving for side S, I have to use angle S. Sine of 51 degrees, angle S, over lowercase s, which is what we're solving for. So really there's two problems in one here. This proportion is going to help me solve for side T. This proportion is going to help me solve for side S. We're going to cross multiply 13 times the sine of 66 degrees equals t times the sine of 63 degrees. To solve for the length of t, we're going to have to divide by the sine of 63 degrees. And so we're going to put that into our calculator as 13 times the sine of 66 divided by the sine of 63. Make sure that if you're not getting the decimal answer I have, your calculator is in fact in degree mode since we're working with degrees. The nearest tenth would be 13.3. So the measure of side T is 13.3. I'm going to put that up here. To solve for side S, we're going to cross multiply. So we have S times the sine of 63 degrees equals 13 times the sine of 51 degrees. We solve for S by dividing by the sine of 63 degrees. So we're going to put this in our calculator to get this by itself. So we have, compute that to find the measure of angle or side length S. 13 sine of 51 divided by sine of 63 is 11.33. So to the nearest tenth, 11.3. The other angles inside were already given in this triangle. We found the remaining three. We solved this triangle. Three were known. We found the other three of the 6 values in the triangle. Let's take a look at letter B. See if you can set up ratios to solve this triangle. In this triangle, we don't know the measure of angle K, or the length of side K, or the length of side L. So take a moment to pause the video and set up these ratios. All right, here's what we're looking at. Using triangle sum theorem, we're able to calculate 126 by subtracting 29 and 25 from 180. Sine of 126 over side K is one of the things I can solve for is K. But I have to have an angle, a known angle, and opposite side. The known angle being 29 is opposite side, knowing that being 18. So sine of 29 over 18 equals sine of 126 over K. Sine of 29 over 18 equals sine of 25 over side L. Cross multiply, these two will be multiplied, so these will have L times sine of 29, so I have to divide by sine of 29 to solve for L. So we'll have 18 times the sine of 25 divided by the sine of 29. This gives us 15.69, which is roughly 15.7. And we'd already found the measure of angle K to be 126 degrees, so I'll put that there. And now with this one, we're going to cross multiply. These two will get multiplied together. These two will get multiplied together. Those two will stay multiplied together. We'll have 18 times the sine of 126. But we're going to be dividing by the sine of 29 again to get it away from the K. You can expand that if you need to write out the multiplication. 18 sine of 126 divided by sine of 29 gives me 30.03, which is 30 for that side length. This is how law of sine works. In both of these cases, we were given two angles and one side. And in both these cases, that was angle, angle, side, and angle, angle, side. It's also possible for us to have angle, side, angle, and still just be able to set up the problem like we did for finding this angle using the triangle sum theorem. However, there is some times where we're going to have to be concerned when we're using law of sine. If you remember back to geometry, you were able to use side, side, side to prove triangles are congruent, and side, angle, side, and angle, angle, side, and angle, side, angle, and there was something called hypotenuse leg. But there was one thing in particular that you could not use to prove triangles were congruent, and that was angle, side, side, or putting it backwards, side, side, angle. And the reason why, and I'll draw a picture for you, this is the ambiguous case, was that if you had a known side right here, and or a known angle, and then a side and another side, it was very possible that you could draw another triangle with that same angle, this same length side, and this same length side, that was not congruent to this one. I could draw another triangle exactly like this, and it would be congruent, but not by angle, side, side. And the reason being that I could pivot this side right here to come inward, having the exact same length as it did over here, still having angle side side, but now I have this triangle in purple, an obtuse triangle. Whereas my first triangle, the big triangle, is not at all the same size. So I, in fact, have two different triangles that have these legs and this as an angle. So it is possible to have two triangles if we have an angle side-side case or side-side angle case. It's also possible for us to have a triangle such that maybe the first angle is obtuse or larger, and so it will force there to only be one triangle. So we might find, and you'll see how we can tell that in a second, that there might be only one triangle, which is what we expect when we do angle side angle and angle side and all these other things. We expect that we're only solving one triangle. But if this is the case, there is the possibility that there could be a second. There's also one other possibility. We lock this angle, let's say I have this angle at 65 degrees, and this piece right here is 8 centimeters long. And now I have my other side given to me to be 5 centimeters long, or even 7 centimeters long. Well, I can't move this line up because this angle has been locked. And I can't extend this because that side has been locked in terms of its length. This last side doesn't have to be this long. I could put the point here or here or here or anywhere. But as I try to swing this down to meet this side here, it never will. It'll fall upon this side and it won't create a triangle. It'll just create a line. So given an angle like this and these two sides, it is possible that there is no triangle and therefore no solution. So I'll give you a visual example of how we may have no solution and how we may actually have two triangles to solve. In your textbook for lesson 4.7, there are 3.5 algebra rules that we can use to determine which type of solution we're going to have. One triangle, two triangles, or no triangle. And the only time you have to worry about these things being possible is if we're given an angle and two sides, or two sides and an angle, and they look like this when we draw it. It is angle side side when I draw it, or side side angle. You can look at the algebra rules, memorize them if it's helpful to you to know when. For my geometry students, for the purpose of this video, we can go over the rules in class, but for the purpose of this video, I'm going to tell you that if you have a case of angle side side or side side angle, to assume that there might be two triangles. And in attempting to solve those two triangles, you are going to either find out that there are in fact two, or just one, or perhaps none. So let's take a look at this example. We have this picture, 94 degrees is our angle. Okay, so here's what I do. If you're going to draw the picture this way, I'll show you another way to do it in class. But when I have an angle and two sides, if this angle and this side are across from each other, if they're opposites, doesn't matter whether it's A, B, or C, they share the same letter, then they are going to be opposites. And we're going to have the angle side side case. So I'm going to put my known angle here. In this case, it's 94 degrees. Side A is opposite from it. Side C is touching it. And this is side C. So this is going to be the first angle that I find. That means that what's left is side angle B and side B. Now, before I even get to the next thing, I'm going to draw the triangle for this case. I don't know. I haven't measured these angles. I'm not worried about it. I'm just drawing the same thing. This will be the angle I know, 61 degrees. Opposite to it is side A, 9. Since I know segment D is 11, that makes this angle B. That's going to be the first angle I find. Makes this angle C. So I'm going to do the sine of 94 over 15 equals sine of C over 12. I'm going to get my angle and we're going to see what happens. And then on this one, we'll set it up in a second. So I'm going to cross multiply. I now have 15 times the sine of C equals 12 times the sine of 94 degrees. I divide by 15 to get sine of C, which is supposed to be a ratio of 12 times the sine of 94 degrees over 15. The problem is I don't really care what sine of c is. I want the measure of angle c. So how do I undo the sine function? I use its inverse. Or to put it another way, you're solving for the angle. So to find the measure of the angle, you're going to have to use the inverse. What am I going to take the inverse of? This ratio right here. That sine of 94 is not an inverse. It is a ratio for the of sine for an angle of 94. So I have to leave that one as regular sine. I put it in my calculator like this, again, making sure my calculator is in degree mode. The sine inverse of 12 times sine of 94 divided by 15, close parenthesis, gives me 52.9, rounded to the nearest degree is 53 degrees. I'm going to keep a tab of my answer up here. The measure of angle C is 53 degrees. All right, if that's the case, then this angle up here, 180 minus 94 minus 53, is 33 degrees. And using that 33 degrees, I can find side B. However, if it's possible, I don't know if it is yet, for me to pivot this 15 here, then this creates an isosceles triangle, which means that this angle right here would also be 53 degrees. And its linear pair, being supplementary to it, adding to 180, 180 minus 53 would give me an angle right here of 127 degrees, possibly creating another triangle. However, some of you already know that this obtuse triangle cannot exist, because when I try to find the angle B up here, 127 plus 94 is already more than 180 degrees. So it is not possible for me to have a negative angle. So in this case, this triangle can't exist. Only one triangle exists. Let's take a look at letter B. I've drawn it this way, but notice that if I were actually to lock that 61 degree angle, and this side were 11, 9 would be shorter than that and would never reach this side down here. So this would be no solution. However, when I go to solve it mathematically, because some of us just draw triangles and go on autopilot, I'd be saying sine of B over 11. And so what I would have is 9 times sine of B equals 11 times sine of 61 degrees. By dividing by 9, I would have sine of B. Well, I want you to see something. Over here we had 12 times sine of 94 divided by 15, which was a ratio of 0.79. That's not an exact value on a unit circle, but remember that on our unit circle, sine fluctuated from -1 to 1 and back down to -1 as it spun around the circle. And doing sine inverse was from, well, we haven't talked about that yet. We will be. So the idea is sine's ratio can only be up to 1, a high maximum of 1, and a minimum of -1. If I look at this ratio, 11 times the sine of 61 degrees divided by 9, I get a number greater than 1, which is not possible. Sine cannot be that ratio. It has to be between -1 and 1. And so this is not possible, and your calculator will tell you that. When you try to do the inverse of 11 times sine of 61 degrees and divide it by 9, your calculator will have a domain error. We'll talk about why that's a domain error later. But for right now, we get an error. And the reason is it's impossible to do the inverse of a value that's greater than 1 for sine or for sine even. We're going to jump to the other case of the ambiguous case. So right here, you can see why there was only one solution. We have this 127 degree angle and 94 adding up in that triangle does not work. But this main triangle here worked. We could solve for B using law of sines. In this particular case, I went back to A because I forgot to finish it. B was 33 degrees. So sine of 33 degrees over side B equals, again, I had the 94 and 15 to start. So sine of 94 over 15. Cross multiply and solve. So I have 15 times sine of 33 divided by sine of 94. And I get a side length for B of 8.18, so 8.2. And only one case. We're going to take a look at how to solve it when there are two cases. So if you go to the ambiguous case, when there are two cases, we're going to look at letter A. I'm going to draw, again, the same picture. Because it's an angle on two sides, I'm going to start by drawing my picture like this. Okay? And the unknown angle will go here. It doesn't have to be A. It could be any letter. It's the known angle. The opposite side is 8. Side B is 10, which makes this angle B and this angle C. Now I know that it's possible that we could have another triangle. So I put an 8 here. For those of you who are visual, this picture will make total sense, and as you solve, it will make sense. For those of you who are not, you're going to want to do it a little bit differently, and we'll talk about how in a second. So I start just by solving the purple triangle. I want to find angle B. It's opposite of side 10. So sine of B over 10 equals sine of A, 38 degrees, over 8. This times this divided by 8 equals the sine of B. 10 times the sine of 38 degrees divided by 8. That ratio is going to be less than 1. I know that already, but you can put it in the right calculator to try it. This means the measurement angle B is sine inverse of this right here. 10 times the sine of 38 degrees divided by 8. For my calculator, I have 10 times the sine, or actually sine inverse, of 10 times the sine of 38 degrees divided by 8. This gives me 50.3, rounded to the nearest 3 is 50 degrees. I'm doing this because there's two possible triangles. So I'm going to write case 1 and case 2. Case 2 might not exist, so I may end up crossing it out. In case 1, I have to find measure angle B because I don't know it. I have to find measure angle C based off of measure angle B, and side C based off of measure angle C. We just found measure angle B to be 50 degrees. However, it is possible, so I'm going to draw that triangle over here. I now know that B is 58 degrees, that A is 38 degrees, that side A is 8, side B is 10. All that's left to solve in this big purple triangle is side C and angle C. And I can use side C and angle C. And I can use a couple different methods. I can use get that, and we'll look at that. Actually, law of sines and triangle sum. However, here's the problem. If this is 50 and I had pivoted this 8 side 8 over here, this would also be 50, which would make this linear pair, which has 180, this angle here has to be 130 degrees. So now I have this blue triangle as a possibility that maybe instead of it being a 58 degree angle, angle B, we'll call it B prime because it's a different case, could actually be 130 degrees. Angle A would be the 38 degrees. Angle C would be something smaller than this angle C because you can see it's a portion of it. And don't forget, side A was 8 right there. I'm taking this triangle and drawing it here to separate them. Now I have two triangles to solve. I have to solve for angle C and side C on both of these. This I'll call C prime. So notice, how did I calculate this 130? I took this first angle that I found, the 50 degrees, and took it away from 180 to get this angle. If I took this and did 180 minus 50, that gives me measure of angle B prime to be 130 degrees. That's how I get this case 2. And after that, two sides don't mix. I solve this triangle separately. I solve this triangle separately, which is why I've drawn separate pictures. In this triangle, the purple triangle, 180 minus 58 minus 38 is 84 degrees. I should probably do that in purple. 84 degrees for angle C. So now I can solve for side C by doing sine of 84 degrees over C equals the original one I was given was the 38 degrees, and that was over side 8. So I'm going to cross multiply and solve for C. C equals 8 times the sine of 84 divided by the sine of 38. I'll have to put in parentheses in my calculator. 8 times times sine of 84 divided by sine of 38. This gives me a side length of 12.92, which rounds to 12.9. I have now solved the purple triangle, the big triangle, the acute triangle case, where the angles are 50, 84, and 38. And we can see that in this purple triangle here. But because this leg could have pivoted, creating an obtuse triangle, I also have to solve the possibility of the obtuse triangle. In that particular case, 180 minus 130 minus 38 is a whopping 12 degrees for angle C prime. So C prime is 12 degrees. Because angle A didn't change, it stayed 38. Side B stayed 10, side A stayed 8. But this different angle is going to give me a different side. So now in order to solve for that triangle, I have sine of 38 degrees still over 8. But as I solve for angle C prime, I have to put that over its opposite side C. And C prime, actually I already know C prime is 12 degrees as I solve this blue triangle here. Cross multiply, I'm going to have 8 times sine of 12 equals C times sine of 38. I'm going to divide by the sine of 38 to solve for C. So I have 8 times sine of 12 divided by sine of 38. This gives me 2.7. In review, I drew my main triangle. I found this angle first. I redrew this triangle without the pivoted leg so that I could solve just that triangle. I used the 50 degrees, taking it away from 180 gave me the 30 degrees to create this obtuse triangle. Same angle A, same side A, same side B, but a different angle for B, called B prime. Subtracting that from 180 let me find angle C prime, and then using law of sines to find side C. So once you have your first angle and its possible alternate angle, those create two separate triangles. You have to solve them separately. Let's take a look at this for letter B. That will be the last example in this video clip for law of sines. For side B, or for letter B, we have a triangle. I'm going to draw it like this because it is an angle in two sides, and one of the sides is opposite of that angle. All right, so this gets me. All right, so we've got angle A is the known angle, so I put that known angle here. It's opposite side A here. The other side here. And so that makes this angle B. I can call them any letters I want. If these two letters are opposites, the angle goes here, the side goes here. So in this particular triangle, sine of B over 57 equals sine of 65 degrees over 55. Angle over opposite side, sine of the angle over the opposite side. To solve for B, I'm going to multiply this. This will be divided by 55. So sine of B equals 57 times sine of 65 divided by 55. And that's 65 degrees. To find measure of angle B, we have to do sine inverse of this whole thing to find the measure of angle B. And again, we're going to have two possible cases. When I see angle side to side, I'm going to try to see if I have two cases. I may have none, which I'll get the error on my calculator. We saw that. Or I might go to case 2 and it might not exist. But in this case, I think it's true because that's the example. So sine inverse of 57 sine 65 divided by 55 is 69.9 or 70 degrees. So the measure of angle B is 70 degrees. And that's in this triangle. Now, because there's the possibility that this leg of 55 pivots over to here, that would make this 70 degrees because it's an isosceles triangle. These angles have to be the same. 180 minus 70 would be 110. Let's see if that'll even work out. So here's what I'm going to do. I'm going to redraw this blue triangle as one of the things I'm solving. That's my case 1. So in that triangle, I have 65 degrees, I have 45 that was given, 57 that was given. We just found 70 degrees. We're going to have to find angle C and side C. In this obtuse triangle in pink, this is 110 degrees. This is still 65. This is still 55. This is still 57, because those are that were given 110. And this is B prime, the alternate triangle that could be created, which makes this C prime. The skinny angle should be smaller than this angle of C. So in this triangle, we have to find, in the two triangle, we have to find angle C and side C. In the pink triangle, we already know B prime, that's 110. We have to find measure of angle C and length of side C. Measure of angle C is easy. In this triangle, I just do 180 minus 70 minus 65 and get 45 degrees for angle C. In the pink triangle, I do the same thing, 180 minus 110 minus 65, and I get positive 5 degrees. If I got a negative angle, that would mean that case 2 did not exist. I could cross it off and just continue to case 1 and be done with one triangle. But because I did get a positive angle for that, there is another case here where angle C instead is 5 degrees because angle B was obtuse. So once again, in the blue triangle, I'm going to solve for side C by doing sine of 45 its opposite angle over C. Sine of the original, oh, this is the A. Sine of 65 degrees over 55. And I'm going to cross multiply. So I'm going to do this times this and divide by that. 55 sine of 45 divided by sine of 65 degrees. This gives me 42.91. So 42.9 is a good value for the side C here. Look, angle C was smaller than C. I'm going to see side C being smaller than side C. C prime should be smaller. So here's side C prime on our pink triangle. On our pink triangle, we've got to go through the same steps now that we know what C prime is. Sine of 5 degrees over side C prime equals sine of 65 degrees over 55, the opposite side. When I cross multiply, I have C prime equaling 55 times the sine of 5 degrees divided by the sine of 65 degrees. 55 sine of 5 divided by the sine of 65. This gives me C prime 5.28, which rounded to the nearest hundredth would be 5.3, or for the nearest tenth would be 5.3. Definitely smaller than the original side C, which is much longer. So we have two cases that we have solved for. I'm going to ask you to try problems C, try letter C, see what you get, try letter D, see what you get, and try this letter C, and I will have those answers posted or in a separate video clip for you. But this concludes the examples for law of sines. Remembering that we're just doing sine of an angle over its opposite side equals sine of an angle over its opposite side. However, if we're given two sides and an angle, we have to be careful how we draw our triangle, because it's possible to have one, two, or no solutions.